Okay, thanks a lot for giving me the opportunity to speak here. I will try to bridge a bit the gap, and I will touch upon some things that have been already explained. I have to apologize. Yesterday I was not here. I was nicely sleeping in my bed, owing to the jet lag. So I might be just hinting towards things that have been said, but okay, some rehearsal is always good. So we all know what we are talking about. We are talking about this evolved HEB and red supergiant stars. I don't have to explain too much to this audience what this means. We are looking really towards these stars that are cool and are extremely luminous. And from observations, we have seen that they exhibit very nice stellar winds. And you can see one of these beautiful images taken by the Hubble Space Telescopes now on the right by Hans Olofsson. And so that picture has really shaped our minds, being these are simple winds. They are one-dimensional and we can live with that. And they are, as such, a beautiful laboratory also to start to study the chemistry. Since if dynamics is easy, well, we can much better look into the understanding of these more complex, often processes of the chemistry. And if we then are doing that in that one-dimensional picture, you see here a schematic to the right that is roughly explaining to us what are the main ingredients. We have the pulsations of the star. They allow the cooler regions to be formed. There we can have dust. On the dust, you have the radiation pressure. The dust is driven out, drag along the gas species, and we get these stellar winds. Mass loss rates, 10 to the minus 8, 10 to the minus 4 solar masses a year. Velocities 5 to 20 kilometers per second, sometimes even higher. And today I will just focus on that one main ingredient, being the mass loss rate, since this is what is driving stellar evolution. Now look to these very simple slides. Isn't it very simple, two colors? What do you see here? This is just a very simple schematic. The mass is fixed to the left, the temperature is fixed to the right. And whenever a mass loss rate would be in the blue zone, the wind is dominating the stellar evolution. When the mass loss rate is lower than that, it's the burning that is dominating the stellar evolution. And we know that most of our HEB stars have easily mass loss rates above 10 to the minus 7 solar masses a year. So just a simple schematic telling you whenever you have such a mass loss rate, this is what stellar evolution is doing, and this is what all our beloved population synthesis codes are just assuming. You put in a mass loss rate and you look what is happening to the life of a star. Now, how has these mass loss rates been derived? Two main methods. We either are looking to spatially unresolved carbon monoxide lines, have been discussed already a bit today, or we look to spectral energy distributions where we see the dust. And above we see the gas species. And people have been modeling a lot of this data to deduce relations. Relations that tell them, given what they know, sometimes of the mass, but most often on temperature, luminosity, a bit on chemical species, this is the mass loss rate. And if you do that for a lot of stars, you get a kind of an analytical relations. You see here two of them at the bottom of the slide. One by Jacob van Loon, one by Stephen Goldman, that give you different relation. And that's so easy. When you have such an analytic relations, this is what astronomers like. You know, it's simple. You can understand that, at least you think, but you put into a lot of physics and chemistry that often you don't understand. This is what our MESA codes are using, for instance. However, if you're now plotting all of these relations that you can't find in the literature on that same graph that I just have been showing you, this is what is actually happening. Each of these people think they have the truth. But if you look to the differences between each of these predictions, you can see orders of magnitudes. So depending on whom you're believing, your stellar evolution codes will, for instance, predict that your HEB star comes much faster to the end of its life than when you would opt for another mass loss rate to be used. So it's a kind of a tuning parameter, and people seldomly explain what they have been tuning to, but they use the one that this just fits them best for whatever reason they might be thinking about. But then the main question that we then want to address, all of these people have really done a big effort into getting Maslow's weights. Why do we then see that huge differences, orders of magnitude? Well, there is a very big elephant here in the room. And that's this one. What is the real life of an aging star? That's the real life. We have seen this picture already. A real star is not spherically symmetric. You have these convective bubbles. If you look a little bit further out, you see also that when you are studying the dust species, also there I don't see sphericity. And then this is one of these ALMA pictures of the Atomium project. This is one of our beloved objects, and we are so happy when we have seen that. You see this AGP winds. This one has a clearly bipolar outflow. Right? That's the red and the blue part that you can see. And then already touched upon slightly by Shazreen this morning, when these winds are colliding with the interstellar medium, as you can see here, you get this bow shock-like structure. So all of our beliefs or all our methods that we have been using to deduce Maslow's weights are just too simplified. So this one-dimensional framework is just not what we should aim for. We have to embrace the three-dimensional complexities, not only of how dust species are forming and the gaseous clusters, the things that Marie, for instance, is so concerned about. We have to understand what is happening at the surface, and we have to understand what is shaping these stellar winds. Only then we might have a potential to understand the real Maslow's weights of these stars. But stars are seldom alone. Now, this is one of the things I have been showing you already to you. This should be one of these carbon monoxide lines that we have been observing in the past. And we have done that for many stars. And then we have now been using ALMA to look again at these stars. And when you do that, this is what you see. This is Eraquile, and Eraquile clearly, maybe I'll try to do it again. This is what this line profile is hiding. A line profile is just hiding the complexity of the density. This is the Atomium postcard we have been making. None of them shows us nicely spherical symmetry. Sometimes overall you have it, but you have these complexities in kind of an arc-like structures, bipolar-like structures. These are weaker spiral-like structures, but they are there. By the way, remember, I come back to that one. We have seen that. It is the same physics that is causing both AGP winds and planetary nebula to be not spherically symmetric. And when looking at these AGP stars, we have caught the mechanism into act. But what you can see here in that picture is not randomly ordered. It's not by me choosing that these stars with spiral-like structures are at the bottom. I could have chosen that, but I haven't. The only thing I did here is I have used one of the properties, rough properties, the Maslow's weight, to order them with the lowest Maslow's weights here at the top and increasing going to the bottom parts. And there's a clear correlation between Maslow's weight and the morphology, and even better if you would include here the expansion velocity. So it's not a two-dimensional axis, you have a three-dimensional diagram. The cause of that, binarity. But, as already pointed out earlier today by Shazreen, we should not only look, and this was what we thought in the past, towards close binaries, which are orbital periods lower than a few days, but also to wider binaries where we have orbital periods of a few years even. I don't have to touch on that. This is what Shazreen have been showing. What is then happening is that you can have, and this is the second diagram, that the wind is filling the row slope, and that you can get, for instance, tunneling via L1, and you get an accretion disk form. As of that, and thanks to also the ALMA observations, people has really restarted the business of doing this kind of hydrodynamical simulations, as Jolien also have been showing yesterday. We are trying now to understand why and how we can get these morphologies. What can we see? How do we have to model that? And is there a link between models and real data, since data don't lie? And this is the most beautiful image, I think, of Jolin's PhD thesis, where we have, where I have shown that already, you have this very nice snail-like picture in this system that has 3 stars. But this is density. What I see in my data as intensity. So we have to do the radiative transfer there. And we all know that this can be very much time consuming. So Frederik de Keuster from the KU Leuven has been developing the Magritte code. It's open source. You can get it on GitHub, which is a very fast code to do radiative transfer, even for complex morphologies, both for grid-based and for SPH-based codes. And if you do that, and if you use that code, you see now to the left one of these hydro simulations with pulsations. This is the thing that you see in the center, where you have all of these little smaller rings here. You have the companion. And so when we wait a bit, you see also then that he's predicting what kind of profiles we have. And then comes also the tilting. What happens if we change the inclination axis? And just from that one simple exercise, you can see that, first of all, density and intensity is sometimes very difficult to link mentally. What can I see? How can I translate that? Let alone if Malcolm is talking about his mazes, I can, or for me at least, it's almost impossible to link one with the other if I haven't done it in the forward way. And then the question, can a partner change your life? Yes, it is. Is it dramatic? I'll leave it to you. Since why? This is one of the simulations, this is the same one, I'm just showing you. If we do that, everything up as well as possible ab initio, we get the mass loss rate out. We have there a mass loss rate around 4 times 10 to the minus 6 solar masses a year. Now, we do the same simulation, but I don't have the partner. And then, what kind of mass loss rate do we then get? It is lower. It is lower by here, that case, roughly a factor of 6. And as you can see here, the partner is at 10 astronomical units. It's close in, but also not too close in. So Charles Leen was mentioning a factor of a few. This is a star which is roughly 0.5 solar masses. If I would do that for a star which is 1 solar masses, we expect to see a difference of at least 1 order of magnitude between having a simulation with and without a partner. And having a higher mass loss rate, so having a partner, is shortening your life, since you lose your energy, whatever here, your material a bit faster potentially. The main conclusion here is that we have overestimated these mass loss rates in our cellular evolution codes. We are just wrong. So what are then the implications? If your mass loss rate is too low, you can think of many things that are happening, and I will not discuss all of them, but it impacts how planets can be forming. It impacts the enrichments of the interstellar medium. It impacts our carbon budget, etc., etc., etc. And then all dependent, so you can also see conflicts there in the reasoning, all depending on which path you're forming, you can have, for instance, have fewer planets, and you can have also more planets. It all will depend on what will be the dominant pathway in this complex graph. And then you can say, and you can agree, I hope, with me, there is a problem. But if there is a problem, we should try to think on a solution, how to tackle the problem. Oh, okay. It's non-ideal, what I will propose you, since we are living in this non-ideal astrophysical scenario. What do I mean with that? First of all, we have a lot of spectral energy distributions, thousands of stars. We love them. We use them in the galaxy. We use them in the Magellanic Clouds, and we are analyzing them, and we get mass loss rates out of that. However, there we have to deal with the unknown dust velocity, with the unknown dust to gas mass ratio, and we are mainly tracing the warmer dust close to the star. And we have seen that this is exactly also where we have the overdensity owing to the spiral arms that are forming. So don't use spectral energy distributions if you want to estimate the mass loss rates. Okay, let's do the other thing. Gas species. So not dust, gas. We have fewer stars there, but still above a few hundred. And then you have all of these carbon monoxide lines. We analyze them with our radiator transfer codes. This is one of the pictures of Elvire de Beck. But if I now use these same stars and I go to the channel maps for the closest ones, I see that, they are not very symmetric. So how to use information that is hitting there, very useful information, but I'm lacking details. But I can also, having a mass loss rate based on the channel maps, I only maybe have 20 sources for which I have good channel maps. So this is the non-ideal scenario. Either you have a lot of data, but you hide the information, or you have a few sources where you have all of the information available, but the few is not enough to get a good insight in what is happening. So this is now one of these examples. I just told you WX Piscinis or ERC 10011. Remember that one. And it's good to always refer to yourself when you make a mistake. This is my paper.
Just a few more, well, a minute or so. You're really going over time, just so you know.
I will. I still had a solution to my problem. Can I propose it?
Yeah.
Okay, I'll do. This is WX Piscinis, carbon monoxide lines. I could not predict it with my one-dimensional model. So what I have been doing, I thought I was clever, I have been introducing changes into the mass loss rate to explain the complex profiles. And then we looked at the data with ALMA, and it is a spiral structure. So what I had been proposing in 2007 is just wrong. Okay? So I want to give still the answer, Marie, if you allow. We have now put forward, or at least we have put it forward for one of my PhD students, a plan that exists out of 6 steps where we hope to improve the mass loss rate. So how to do that? First step. Step 1 is we have these 3-dimensional pictures. And Owen Vermeulen, that's a PhD student, has been running a lot of radiator transfer profiles and trying to understand and visualize what is the difference if I would have done things in 1 dimension versus 3 dimensions. We start to get a feeling on what is the hidden information in the lines. Second step. What he then has been doing is we have now this information. I just hide the channel maps. I only have now the line profiles. And then Frederik de Keuster, the same of Margriet, has developed POM. POM is just the inverse of Margriet. It just, you can give it a line profile, and it uses a probabilistic method based on Bayesian statistics to tell you, okay, but that might then be the densities, the velocities, etc., for the framework that you choose. That's the example in 1D. And we have done it already in 3D. So that's so good, we don't have to do the forward model, we can do the retrieval directly. Step 4 is the observations. We have these reconstructions now. This is data to the left, and this is a reconstruction of the CO density to the right. We can start seeing what is the density given, that's still a given velocity information. And the last step comes to the mathematics. Leuven is producing a lot of CO line profiles where we see signatures of binarity, interaction binaries versus single stars. We will be developing a method based on a support vector machine that will tell us, is it a binary or is it a single star? It implies, I can discuss that in detail, how you can do that. It implies mathematics and finding an orthonormal basis in that. And that will then allow us to develop the predictor. Given something, it will tell you interacting binary, single star, and it will give you then the predicted Maslow's weight. And the last step is there. When we have developed that, I hope in 2 or 3 years' time from now, we can apply it to all of our data. We have mainly then the line profiles, and it will pick out the stars of which we really know this is a single star. It will give you a Maslow's weight. It will also give you the Maslow's weight for the binary stars, but with a higher uncertainty there. And now I know I have had too much of time, but at least I hope to have put forward a way to tackle that.
In most of these observations, what am I looking at? So the options are wind interaction, or an object has already gone in, it has not unbound the envelopes, you still got your AGB star, and what you're seeing is the aftermath of that operation that has happened. So Roche-Loeb overflow would be a very fast phase, so it's unlikely we catch it in the act, but the wind interaction or the aftermath of a merger that's happening inside the common envelope could be options. Yes,
but you will, it all depends on the scale. So you have seen here pictures that are taken that have a size of a few astronomical units. That's typically the scales that we see for this more what I call the wind interaction when you have the wind Roche-Loeb overflow situation. But you will have the similar situations and when you have had the merger, etc. Absolutely.